In this video, we're going to be proving the formula for the area of a triangle using trigonometry. So we're going to start off by drawing our arbitrary triangle, and then we're going to label up the sides and angles according to their opposite pairs. So the convention is to use capitals for angles, so I'm going to do capital A for the bottom left angle, and then small a is the opposite side. And then we've got capital B and B, and then capital C and C. So that's how we're labeling up our triangle. Now our aim is to get a formula for the area of this triangle using just the 6 quantities that we've got there. So to start with, we're going to note that the area of a triangle is a half times the base times the height. The base is already given, that's our small b, but the height isn't currently on the picture, and it's something that we need to get in terms of these 6 things. So our area is a half BH, where h is this perpendicular height given there. Okay, so now you'll notice that we've chopped our triangle into two separate right-angled triangles, one on the left, one on the right. If we use some SOHCAHTOA, then we can get an expression for h in terms of the other letters. So on the left side, if I consider sine of capital A, then that's going to give me opposite side, which is h, over the hypotenuse, which is c. And if you look at the right-hand side, you're going to get sine of c, which is h over a. Notice I can't use cos because b is divided into these 2 unknown quantities on the bottom. So both of these I can rearrange to get h on its own. So you've either got c sine a equals h or a sine c equals h. If you substitute that then into your area formula, if it's a half base height, then on the one hand you've got a half b c sine a, and on the other hand you've got a half b a sine c, which you'll notice rearranges immediately into our half ab sine c. So that's our formula proved. In 2 out of the 3 cases that we like to consider, we tend to write it in this form as a half ab sine c. But you've got to note that however you've labelled up your triangle, the angle that you use for C has got to be the one in between the sides A and B. So in other words, to use this formula properly, you've got to make sure that you've got what we call an SAS, which is going to be a side, and then the included angle in between, and then the other side, like this. Okay, so our formula is proved then. It's proved for these 2 cases. I'll leave it to you to show that the area can also be written as a half AC sine B, which is the remaining form of these 3. I'll leave you to draw the picture as to how that's going to work. It's to do with drawing this perpendicular drop in a different place. But also, we've got to make sure that this is going to work for any triangle. And in particular, I've drawn this triangle as an acute triangle. So because all of the angles given are acute, that means that we can easily drop this perpendicular height down to the base. But if our triangle is obtuse, that's not quite going to work the same way. So let's finish off by doing this same idea and getting the same formula but using an obtuse triangle. Okay, so I'll start with drawing a nice big obtuse triangle as best I can. Okay, as straight as I can possibly do, and we'll label up the angles and sides in the same way. We've got A, B, C for these angles, and then we've got the opposite sides as well, A, B, C. Okay, so because of this obtuse angle A, I'm not going to be able to drop a perpendicular down onto the base this time, but what I can do is drop the perpendicular down from B until it's in line with the base, and then extend the base outwards this way. So I've now got a new right angled triangle here in this space on the left, and our aim is to get a similar expression for the area in this case. So what I can firstly do is I can put the height on the triangle here, and then because of the triangle that we've got on this left side, I'm going to need to consider this angle in here. So if the obtuse angle here given in red is capital A, then on the straight line it looks like this is going to be 180 degrees minus A. And then if the area of the triangle that we started with is a half times the base times the height, so we've got base here and then this height here, I can do something in this left-hand triangle to get an expression for h. So it looks like h is going to be, well, I can think about sine of this angle. So I'm going to start a new line. Sine of 180 degrees minus A equals h over c. So now I've got to think about what I can do with this expression here. If I've got 180 minus A, what happens to the value of sine? Well, let's draw the value, I should say the graph of sine, and we'll see what happens when you do that. So here's my A for my angle. The sine graph looks like this. So at the middle here, you've got 180 degrees, which is all we need to get angles inside a triangle. And then there's a line of symmetry here at 90 degrees. Okay, so what we need then is we need to link A with 180 minus A. So if my obtuse angle here is A, somewhere between 90 and 180, because it's obtuse, then the value of sine, which will be something positive like this, will give me something there. And if I reflect in this line of symmetry, I'm going to get 180 minus A, which is somewhere down here. Okay, 180 minus A. Now you notice that the values of sine that we're going to get are exactly the same. So that means that our formula is still going to hold, because sine of 180 minus A is the same as sine of A. Okay, so our formula is going to be exactly the same if we've got an obtuse triangle. You can finish off the steps, solve for h in here, and then stick it up here, and you're going to get a similar expression for the area. Okay, so that's our proof fully complete. We can now use trigonometry to get the area of any triangle that we like, so long as we've got an SAS. Okay, thanks, Year 12. See you soon.